Thank you very much. Hi, everyone. So I will talk to you about my PhD activity during these 3 years by the title Video Streaming and Video Surveillance in Mobile Scenarios. The activity I carried on was focused on what we call mobile video surveillance, and the first year was focused on enabling video surveillance through effective video streaming, so carrying video data from one source to the other through the network. And the second and the third year was focused more on video analysis on this video data. And I will try to cover all this, to span over all this research I carried on during these years. So I depicted here a scheme of a distributed video surveillance system, and a mobile video surveillance system is a surveillance system where the modules that compose it, that make it, have a certain degree of distribution and of mobility. So when there is some mobility and some distribution, the system can be defined mobile video surveillance, therefore. And of course, if you are distributed, if you are mobile, the encoding, the video streaming through the network that might be wireless, and the decoding and so on, the error concealment must be effective. And we defined 6 parameters that we want to effectively care to be successful in streaming video from the source to the other modules. That are these 6 ones, like the most important is surely video latency and high image quality, but also video fluidity and others. And we designed and developed a system called Moses for streaming and having care of these 6 points. I will very briefly show you the scheme of the encoder and the decoder, and by the way, they are both available to download at my homepage. The encoder gets the data from a video source, and it passes the data to a video codec based on H.264, the well-known codec, through circular buffers, and then it passes it to a network streamer that goes then to the network. Everything is multi-threaded to be very optimized in performance and tuned to have very low buffer occupancy, because buffer occupancy means latency. So it is important to keep the buffer occupancy very low. And then this is the decoder. You get the stream from the network, you pass it to the decoder based on FFmpeg. Everything is open source here. Nothing is like proprietary. And then you pass it to the GDI plus control to be printed on the screen. And of course, we added here an adaptive control of the playback, because we want to tune the playback in a very slight way to keep the occupancy of the buffer as low as possible, because as I mentioned you, buffer occupancy means latency. So if it is low, the latency will be low as well. Very briefly, I depicted here a few results of our system when it was like encoding from a fixed platform to a mobile, a PDA, for 3 platforms: Windows Media, Real Media, and our system. And you can see that the latency is pretty low in our system compared to the others. And with such low latency, we can achieve even higher image quality. We think that the system is pretty performing, and you can find further details in the transactional multimedia that it was published in 2008. Then let me go over the second part of my PhD activity, that is video analysis. And it was divided into 2 parts as well. The first, mostly covering 2008, on object tracking in mobile video surveillance, and the second, people detection. That was the last year activity. For object tracking, we cared and we tackled 2 different scenarios. The first one was a scenario where there is a high degree of system distribution, and we want to test how does tracking perform, like traditional tracking with steady camera, on very compressed data, and the second scenario is where the mobility is very high, and so tracking with a freely moving camera. And I will talk to you about both. The first one, we designed this system where we have a video repository to make tests, and we dispatch the video through Moses encoder, through GPRS, and through the decoder, and we make this video be processed by our SACbot system that performs object tracking, and we do the same, but on the original video. And then we assess the performance of both, and we can make comparisons. And I depicted here a few results. For example, in this kind of sequence that is, yes, it is outdoor, but basically the conditions are like indoor. There is no lighting change because it is covered. It is here in the hall of the faculty. We can compress up to 5 kilobits. And 5 kilobits, I mean, it's very low. It's like 1/20th of an MP3. Consider that. And we can still do tracking, like with 96% of accuracy, and real media does a bit worse. And when we work outdoor, where there is more movements and more people and more lightning changes, we need to boost up a bit the bandwidth, and still the tracking accuracy is still good. And this is precision and recall at pixel-wise level for motion segmentation. And of course, the more you lean toward this point, 1,1 and 1,1 here, the more accurate you are. So you can see that Moses, the blue dots, I hope you can see them, lean more towards the 1,1 rather than real media. So we are performing better even in pixel-wise segmentation. So let me very quickly go to the second part, object tracking with freely moving camera. So we mean tracking of objects in this kind of conditions where the camera is really moving. You don't have, of course, you cannot rely on geometry, you cannot rely on prior information about the position of the camera because it is zooming. It is not just simply panning or tilting. It's really moving freely. Sharp moves and scene cuts, and the background can be whatever, cluttered. And not necessarily you want to get stuck on the human tracking. So we thought, why don't we isolate features? We try to detect them, and then we lay on top of this feature detection a graph-based theory to maintain consistency of the tracking. And I will try to show you what I mean. So we build up at first a module of the object that we want to track. This is just a depiction. For example, a model made of 3 parts. We isolate the 3 parts, and each of the 3 parts has a structure that could be, in this case, for example, one on top of the other. And each of these parts have a feature. For example, it could be the color, like the head, like pink and blue for the shirt, and pink and blue for the middle layer, the middle part. And then for each frame, you pass the frame through that feature, and you get a probabilistic map. That means the probabilistic presence of that feature in the current frame, and then you scatter some particles, and then for each particle you enlarge it up to enclosing a cluster, so you get a redundant set of clusters, and hopefully one of them will have the real part that you want to track. So it is redundant by definition, and you get some properties from these clusters, like central mass, area, and so on. And then what you do? Then you start with the graph model, the graph theory, and I will try to let you understand what I mean. So we have a model graph that is made of representative parts of nodes, like the head, the neck, the hands, for example, so a semantic meaning, and then they are connected through edges that give the structure of the model. And then for each frame, you define a labeled graph. You have like redundant clusters, as I told you, but each cluster was created by a specific feature. This was created, for example, by the feature of the head, and so on. And then you build, a priori, a p-partite graph. And then the tracking can be translated just as finding the best subgraph isomorphism from here to here. To find this in an effective way, we do a further step. We create an association graph. I cannot go too much in detail, but it is basically a product of the two. And there is a theorem, and in my PhD thesis is demonstrated, there is the proof, where finding the maximum subgraph isomorphism is like finding the maximum edge weight click on this graph. So to do this, we have a framework that we we took from some colleagues in University of Venezia, and they extract this click, and you can transpose it back to the label graph, and as you can see, it is red here. So this is the tracked object. And very briefly, let me show you the video. And you can see here that there is a human model made of 5 parts, like the 2 hands and the legs and torso and head. And when the ellipse becomes green, it means that that part is not really reliable, and it is temporarily suspended. But you can see that, I mean, there is motion, there is rotation, zooming, and in a few seconds you will see that the head disappears, goes out of the frame, and the head tracking is suspended, but then it is started back again in a few seconds as soon as the head appears again. Okay. So let's focus more now on my 2009 research. We decided to face a real world scenario for safety, that is the construction working site. And the videos that we collected on the ground are of this kind of visual type, let's say, with very high occlusion, degree of occlusions, clutter, a lot of smoke and camera vibration, and things are built in front of you in the time span of 1 day. So it's real mess for traditional surveillance system based on background differencing. And for this reason, we decided to avoid object tracking and to try to exploit just appearance. We want to detect where are the people, and we try to look for their appearance only. So the first thing that we did was to implement a pretty well-performing idea from Tuzel and others that exploits a rejection cascade of classifiers. And how does it work? That if you want to classify a patch, understand if it is a human, if it looks like a human at least, you pass this patch to this rejection cascade, and each classifier, he is focused on a specific part of the human, of the appearance of a human, and each one will try to reject or approve it. And if it approves it, the patch goes to the next layer, and so on, up to the point it is rejected. And being rejected means it is not a human. Otherwise, if it is a human, it should ideally pass through all of them and then be classified as a human. And of course, as you understand the performance, the deeper you go inside the cascade, the higher the detection rate on the negative becomes, because you reject more and more. But of course, the detection rate on the positive goes lower and lower, because you risk to reject true positives. So the detection works basically, the traditional way of detecting an object works in this way, that on a frame you extract all possible patches at all possible locations and scales, and you pass them to the classifier, to the binary classifier, that gives you just the patches that have human outlook. For example, here there is a human, but there are also some false positives. The problem of this technique is twofold: the accuracy and the computational time that is very demanding, because it's a brute force approach. So we tackled both. We tried to improve accuracy in our scenario and computational time. For example, the first thing that we envisioned, that we thought about, was that it would be very cool, from a video sequence taken directly from the camera that is processing, try to have something that gives us the idea of the size of the humans inside the frame. And we thought that we could be possible to do that exploiting the pedestrian detector. And how does it do? It works. It works. So we pass a video sequence, for example, at the beginning of the working day, or at the beginning of the week, to the pedestrian detector, that gives us a bunch of detections. And some of them, actually 2/3 basically, according to our statistics, are true positives, like I hope you can see the colors. Like this one is a man, and of course it's a true positive. Some of them will be false detections that are totally out of scale, like this one. It's totally out of scale compared to humans. And other ones, a small portion, will be false detection that are similar size of humans. And then we pass all these bounding boxes, these sizes, and the coordinates of these bounding boxes to a linear square estimator with RANSAC to reject outliers. And we get a nice function that is the height in pixels of the human as a function of the x and y coordinates of the feet of the human touching the ground. And if we apply this function to this set of detection, it keeps just these ones. So it means that it is able to reject all those out of perspective detection. And this is very good because, of course, it improves performances, but it also improves computational time, and I will show you later. But then we had a further idea. Why, since the behavior of the cascade is asymptotic, so the last stages are not as good as the first ones to improve performances, why don't we remove this or retrain this? And actually we do that. We thought we should have something that from a video sequence that we want to work on, from that position of the camera, let's extract some images that will then become a training data set for the retraining of these last cascades. And what we do is, this is a relevance feedback approach. We extract background images that by definition don't have pedestrians that are moving objects. And also, applying the pedestrian detector to this video sequence, we get a bunch of detections. Some of them are true positives, some are false positives, and we ask to a human to assess them, to divide them in true positives and false positives. And all this data creates a new training set for retraining the last cascades, last stages of the cascade. So let's see about accuracy. You see that the precision improves a lot from, this is the precision on an image basis of the original classifier, and this is the precision of the original classifier plus perspective estimation and plus relevance feedback. So you go from 20 to like 70%. And we did also a good job because recall, by definition of a rejection cascade, cannot but decrease. And so, keeping it at the same level, we did a good job, because once you have rejected a true positive, you cannot then get it back, because this is the definition of the rejection cascade. You can find all these things in my PhD thesis in detail. And regarding time, well, consider that applying the perspective estimation, you throw away 90% of the patches, just a priori, because they are out of scale. And you work just on 10%, so basically you speed up a lot, like 10x. And there are a few examples, like just plain pedestrian detection here. I don't know if you can see the green bounding boxes. And when you apply the perspective, of course, this gets cut out. And when you applied also the relevance feedback, even these false positives get cut out. And so you have just the pedestrian there. And then we said, well, why don't we try to apply a Bayesian approach, a Bayesian paradigm to the pedestrian detection, avoiding brute force. Let's try to estimate the presence of the pedestrian like a PDF. And this is what we did with the multistage approach. We start from a proposal. This is a proposal distribution that is uniform. At the beginning, we have no priors at all. We don't know where the pedestrians are. And we start this multistage algorithm. We draw some samples from our uniform distribution. And for each of these samples, we assign a Gaussian kernel. And then we measure each of these samples according to how in deep it goes through this cascade. The more it goes toward the end, the higher is the weight. Therefore, the samples that fall close to the pedestrians will have high weight, and those that fall outside of the pedestrian will have low weights. And even distractors might have high weights, of course. And then what you do, you build up a mixture of Gaussians out of these samples, and that is weighted on the measurements that I just depicted here, and then you update the proposal using this mixture of Gaussians. And then you do it again You do it again, but you sample now from the new proposal that will focus more on the high measurements, and then more, and then more, and then more. And then, of course, at the end, you will retain only the samples that pass through all the cascade, defining a human detection. And these are the samples that gave human detection, successful human detections, and you get the detection of the humans. And this saves a lot of time, because you basically divide by 10 the number of detections to perform, compared to a sliding window. The cool thing is that you can plug this measurement into a Bayesian recursive framework, prediction and update. This is typical. I mean, prediction here from the prior, you get the predicted. From the predicted with the likelihood, you get the posterior. And let me just depict it. You have the prior, and then you convolute with white noise. And notice here that from this frame to the other, a new person entered the scene, and then you use the measurements that I just defined, and see that the measurements don't just get stuck on the prior, because we use a quasi-random sampling, so they also goes there, and then you get, these are the final successful detection from those samples. You get the likelihood out of these. You plug them in the predicted. You get the posterior, and you get the final detections. Just a few results. Our proposal is the MS Boost here. That is that one. It is compared to state-of-the-art classifiers, but consider that they are working with sliding window, and we are working with this sample-based probabilistic approach, like with a third of the computational effort of the others. So we are very, very proud of achieving similar performances, but with like a third of computational time. And let me just show you this video. Consider that here we do not use any kind of background differencing, any kind of motion segmentation, or we don't exploit motion at all. We just exploit appearance and the relevance feedback approach. And we process like at this frame size for 1 frame per second. So it's pretty good. And even when the pedestrians are pretty close, you can still detect them. And consider the visual clutter of the environment. I mean, this is not a nice indoor hallway without distractors. Okay, so I don't know, what is my time? Okay. So this is the list of my publications. A few ones are under review on the last topics I spoke to you about. And so this is all.
Thank you, Giovanni. There is time for a question by the Commission. No question? I have a question. Just on the second topic, the use of graphs for evaluating similarity. If I understand well, because I was, if I understand well, you are doing this similarity comparison for each feature. Don't you think, and so my point is that probably it's important to do the same job with all the features that you think are useful for image comparison.
Well, actually, finding the best subgraph isomorphism tackles all the features together. And because we want to care of the structural model that is defined by the several features together. So this should, I think it cares about the relations between the several features. I don't know if I kind of replied to your observation.
Another point is that when in your presentation you are saying that these are semantic,
Okay.
but it is structural.
Okay.
Okay,
I
just to...
I stepped into somebody else's expertise.
Okay, thank you. Thank you.